Hi there, welcome along to my third live stream on electromagnetic induction, and today we're going to look specifically and only at Lenz's law and how it's used and how you can tackle questions to get all those marks that you are of course really keen to get. So let's jump into it. So good idea to start at the start. First of all then, what we need to do is just revise a couple of quick bits. So this is going to be real quick. So first of all, here is just the bog standard field around a bar magnet. You've seen this loads of times, you of course know it. What's important for us is to remember that if you have a solenoid, i.e. this kind of coil here, so we have a simple coil wrapped around an iron core with a DC, notice DC supply, then that will give us a constant field. We looked last time at describing what happens as you connect the cell, so like if we had a switch here, and how the flux lines builds up. But for now, we're going to be dealing with a constant DC supply. And what we're going to do is take that DC supply, take that solenoid. What we're going to do then is we'll come to that solenoid in a minute, we'll be coming back to that. But first of all, we are looking at a magnetic field there. So, that's good. In this slide then we can see that what we have is a bar magnet. We can see its field that we've grown to know and love, and a simple coil connected to an ammeter. Now what happens is as you move that coil towards the magnet closer together, you're going to get an induced EMF. This you know, you're used to this, you've met it many times. EMF is proportional to N times delta phi over delta T. Remember, delta phi over delta T being the rate of change of flux, and if you're moving the magnet in, you have a rate of change of flux. Suppose you move that magnet in and just leave it stationary. Now the field lines that are enclosed or linked to the coil are constant, no EMF. But this is, in Faraday's law, you'll notice that we have a proportional sign. Now this is something you have to look out for, because often Faraday's law is kind of written with an equal sign. But you know, technically it isn't. Faraday's law is just that it's proportional. Okay, so let's get into Lenz's law. Now Lenz's law, to define Lenz's law is, on one level, really difficult. But if you learn an answer like this, or better still, of course, if you understand an answer like this, then this is really going to help you. So I teach my kids, or show my kids that I teach, I should show, I suppose, this answer, and hope that they will at least adapt it into their own language. So Lenz's law tells us that the direction of the induced EMF, so in other words, which way is the current going to flow in this coil? The direction of the EMF, which way is it going to push the current? Acts to oppose. Now this is where language is really helpful. If you say acts to oppose means to work against, and then acts to oppose means it's going to work against. So the induced EMF works against. Now using a sentence law or statement like that covers a whole multitude of things, so you're not having to be too specific. So the direction of the induced EMF acts to oppose the change that created it. Now the hard part is to try to work out sometimes what is the change that actually created the EMF in the first place. So we're going to do some examples of that. So what you have to do is you have to imagine stepping back into the situation you have. So what actually caused the change? Often it's something like an increase of flux lines or a decrease of flux lines, or you might want to say perhaps it's a movement of a magnet towards a coil, like in our example. Either way, the induced EMF acts to oppose the change that created it, and the key bit is identifying that change. Now in a way that doesn't look too difficult. I've seen multiple questions on the papers that ask you define Lenz's law or state Lenz's law. Now mathematically we're used to saying Faraday's law, N delta phi over delta T. EMF is proportional to the rate of change of flux. Lenz's law is really simple. We're just putting in the constant of proportionality, which is amazingly just -1. And of course, most of the time in maths, if we've got -1, we don't bother writing the 1. So really, we're just putting in a minus sign like that. And what that is showing us is that the EMF acts to oppose the change, i.e. the rate of change of flux, that created it. Okay, so the best thing I think with Lenz's law, learn that and then do a ton of examples. So I'm going to jump into 3 examples now, see how they help us. So the first one then. This is a very common exam style question. You have a coil and you move it. Sorry, you don't have a coil, you have a bar magnet and you move it towards the coil. And that's as you move this magnet towards the coil, we've already seen that as the flux lines are building up in that coil, it's going to induce a current in that coil, an EMF, which will lead to a current if we have the 2 ends of the wire connected in some way, which we have through an ammeter. So we're going to get a current in that coil. And you should know that whenever you have a current in a wire, it produces a magnetic effect. And as we saw right back at the start here, that if you have a solenoid and you put a current through it that's constant in one direction, you will get a set of field lines that look just like a bar magnet. Consequently, if you manage to keep the rate of change constant as you bring in your magnet, which is unbelievably difficult, but just play with it for a minute, what you're going to do is build up a bunch of field lines, as you can see. And so in the coil, as you can see, we've built up a bar magnet pattern again in these pink lines. Look, they look just like the bar magnet. But of course the question is are they going this way or are they going the other way? Or to rephrase that question, let's say they are in fact going this way. That would mean, because you know flux lines go from north to south, that this end here would be a north pole and that end there would be a south pole. You know what, it might be better off actually putting the north and the south right on the coil, because the lines are going into the coil there. Right, so let's just suppose the current, the EMF is flowing left to right, giving us a south there. Well, now we have a problem, because what's going to happen is that we have a north pole at the end of our magnet and a south pole on the right hand side of the coil. Now if that situation were to happen, we would now have a situation where we have a north pole on the end of the magnet and a south pole in the coil, and of course they're going to attract each other. And if they attract each other, the net result of that is there'll be an increased force on our magnet, and that will mean that the magnet will be pulled in, which means that the magnet will accelerate, which in turn means that the rate of change of flux will increase within inside our coil, which means that the EMF and hence the current in the coil will increase. Can you see where we're going with this? And that in turn means that the magnetic field, the pink lines, will increase and move closer together. So in other words, the effect is that if you increase if you move the magnet into the coil, and we get a south at this end, it's going to attract the magnet even more. In other words, it's going to not oppose the change that created it. The change that created it in this case is you or me or whoever moving the magnet in towards the coil. In other words, to build up the flux lines kind of going through the coil there. So what the coil does is produce a set of field lines that oppose that change that created it. In other words, these field lines will be going the other way. Now, there's lots of ways to think about this now. Firstly, if this is actually a north, which is what we're suggesting, then these two norths will oppose each other. So as you push this in, the two magnets will push back a little bit at each other, and you'll actually feel the resistive force as you try to push this in. It's actually real, you can actually feel it. Now that is actually a good thing, because now what you're going to have is you're not going to get in that situation where when you push the magnet it gets faster and faster, because that would break the conservation of energy laws. You could push your magnet in with say 1 joule and it's going to accelerate up to say it's got like 10 joules. It's not going to happen. Can't happen if you're only giving it a flick, say with your finger. So it has to be a north pole. Another way to think about this is that magnetic field lines, as I'm sure you're aware, are actually vectors. So if we have a north flowing this way out of the coil, along with the blue one, which I'm drawing red, from the magnet in the opposite direction, these two vectors are going to cancel out a bit. In other words, you could say the change that's going on here, moving the magnet in, is acting to increase field lines in the coil. So the coil produces field lines that cancel out of that effect by sending them back the other way. So really, this really does obey Lenz's law, which kind of you'd expect really. And yeah, common question this. So let's move on to another one now. One that puzzled me at first when I first saw it, but quickly became able to do it, as you might imagine. So in this next one then, we have a simple coil with one turn here, and obviously a DC supply and some kind of switch. And on the other side we have another coil, a second coil if you like, and the question asks us two things, and we'll consider them both. Firstly, we close the switch. What happens in terms of EMF within the second coil? 1, 2. Well, as you know, as always, just go back over and over again to the EMF formula. EMF proportional to the rate of change of flux, like so. So at the instant you flip the switch, then the magnetic field lines flowing from coil 1 will build up as the current increases, because the current in the circuit, as you flip the switch, time current, suppose you flip the switch at this point here, the current will build up like this until it becomes steady. And this time that it takes the current to build up might only be very short, I don't know, say a millisecond or something, a thousandth of a second, but during that time there's a significant increase in current, and hence a significant increase in flux being produced by coil 1. In other words, we have an increasing flux until we get to this point where the current is steady. Now the rate of change of flux here has become 0, so there's no EMF. So we could kind of draw an EMF graph under that. Just check that's fitting. Yeah, it's fitting. This might be EMF, no, sorry, not EMF, magnetic flux lines, or maybe we should say, how about N phi? There we go. And what's happening now, the N phi is the flux that's created by the first coil, kind of measured in the second coil. So at first, there is none. Then the flux builds up rapidly and becomes constant. But in this little section, we have a rapidly changing flux. So what you find on that bit is that you will get an EMF. So as the current builds up, the flux lines build up, we have a rapid rate of change of flux. You can see that in the first section there. The gradient here is steep, so that's going to give us a big EMF, and then the gradient falls off, meaning the EMF drops off, and then the gradient becomes 0. So the EMF, notice I'm talking about the magnitude of the EMF here. I'm ignoring any sign. At the point where the switch rises, zooms up quickly and then falls back to 0. This probably is not exponential, even though it might look it. It's just downwards curve. So in other words, we can create a spike of EMF in that second coil. So that's the first thing. What happens to the EMF? But the second is what happens to any force between these two coils. Now, this is a bit more interesting, because if you think about Lenz's law again, remember, the direction of the induced EMF acts to oppose the change that created it. There's, again, several ways to think about this. So you could firstly think about it from a current perspective. Well, you know the current is going to flow, let's change the pen colour, is going to flow around this coil in this direction. So that one would suggest that the current is going to be the other way from this coil. Now, without actually committing ourselves to saying which way this is going to be, I'm just saying, let's say this is a north. On the syllabuses, you for the most part don't actually have to be able to say if this is a north or a south, so I'm just going to say it's a north. Now what this means, if the current's going the other way, then if you think about this, the flux lines are going to oppose the flux lines that you're building up. Flux lines building up, we need to oppose those flux lines building up in the second coil. So the current induced in the second coil will have to create flux lines that go the other way. You see how in coil 1 the flux lines are kind of going left to right, whereas in coil 2 they're going right to left. That means that this end too is also a north. That's assuming that this end is a north. Remember we said we can't say for certain at this point. So now we have two norths opposing each other, which of course means if we assume that the coil 1 is kind of fixed, after all it's connected to a power supply, blah blah blah, that means that overall there's going to be a repulsive force between these two coils. Consequently, coil 2 is going to feel a resultant force in that direction. And this, believe it or not, is the basis, or could be used as the basis of weapon systems, for example, causing the magnet, the second coil to sort of shoot off, a bit like a gun, I guess. So that's a little bit harder, that one, perhaps, than this one, but it's following the same idea. Direction of induced EMF acts to oppose the change that created it. Okay, so this was a multiple choice question. Now let's get on to a stonkingly brilliant question. I often do this one with my students, and often at first they go, don't get this at all. But it soon kind of focuses down for them. So what you have here is basically what's known as a magnetic brake. Now a brake, think of a brake on a bike, it's used to stop the wheel spinning. And these brakes can be used in giant machines like trains, for example, or what they call lathes, which are used to spin great heavy pieces of metal round. And you might need to stop the spin very quickly. You can do it like this. I'm not going to go into details about how you would use those in the systems, but we're going to think about why it is that we get a braking force here. So let's attach a little circuit to the brake, just like we're kind of used to. So we have some kind of switch here. So on the lathes that I was talking about, this would be a big emergency red button. You go punch like this, and I've seen this in real life. The wheel, which might be spinning at kind of thousands of revs a minute, punch the red button, stops instantly. And there's an awful lot of force involved here, but these electromagnetic brakes can be really strong. So as we close this switch, clearly we're going to build up a flux through here. Now we don't know, again, as always, which way it's going. We'll just assume it's going the way I've drawn it. And you might think, well, that's nice. We're going to build up a flux which will last for, I don't know, a millisecond. Remember these graphs down the bottom here? Short change of flux because of a short change of current. Yeah, but there's something else going on here. So let's clean off this again. If you imagine little portions of the disc, so this is what you have to do here. So if you imagine like a little section of the disc itself here, so it's a piece of metal within the disc. Haven't labelled that too good, so let's see if I can label that a bit better. A little cross section going through the disc, which is just sitting underneath those magnetic pole pieces. Obviously goes through to the other side as well. Now remember that this little section of metal is turning. Imagine it starts off in a situation where it's got a whole bunch of flux lines moving through it because someone has pressed the magic red button. So as my little red area of the coil there moves out through the magnetic field lines, so that little red area within the wheel experiences a big rapid change of flux because this wheel is probably spinning really fast. So what we're doing is we're breaking the wheel down into little sections and imagining these little sections travelling into the magnet. And as these little sections travel around, so they experience a rapid increase and then decrease in flux, which produces a large force. How does it produce a force? Well, it's the same old story. We know that the EMF induced is equal to the rate of change of flux. Can you see how often this formula comes up? We have a large rate of flux within these little areas of the metal disc. Therefore, within those large metal disc areas, those small areas of disc, we're going to produce some EMF. We know Lenz's law tells us that EMF will act to oppose the change that created it. So what's the change that created it? Well, the change that created it is the spinning of the disc. Without the disc spinning, there wouldn't be any change of flux. The little red bit of metal there would just sit in a constant flux. So think of it as being the turning of the disc that's creating the change. Therefore, the force produced by this EMF, let's just step back, okay? So within each of these little areas, so if I just draw one out here, within each of those little areas, there's magnetic flux going, say, in my case, into the page through these little areas. And so within, so those little crosses, remember, represent magnetic field into the page. So as this moves out of the flux, so it's experiencing a change of flux, because over here there is no flux. That change of flux is going to induce currents within this little section, and those currents might, for example, go this way or that way. Either way, these are the famous eddy currents that you may have come across. So we have what we're in fact doing is inducing currents in little areas of the disk, and those currents create a magnetic field which works to counteract the rotation of the disk. So you're not really, in this question, the mark scheme is interesting because it doesn't really get you to go into great amounts of detail about how those swirling currents produce this force with the electromagnet. It just literally quotes through Lenz's law. So you might write something like, as the coil, no, not the coil, sorry, as the disk turns, right, then you would say areas in the disk. I'm writing this very, very quickly, obviously. Let's just make sure I'm not going, yeah, I'm all right, I'm on the screen still. Areas in the disk are going to experience a rate of change of flux. So we could just put experience, our old friend, rate of change of flux, which leads to EMF and current in the disk, and then disks, and then surprising bit, which oppose the rotation. You might expect that you would need a lot more detail there, but literally just writing in that last little section there is, in this case, surprisingly, all that the mark scheme requires. Actually, in a way, it's not that surprising because it's flipping complicated. But the beauty of all these is that these forces, these resistive forces that you can create between two magnetic fields, can be really, really large. And perhaps in another video, I might show you some stories about just how big these forces can be. So I hope that was somewhat useful for you, and thanks for watching. See you next time. Don't forget to like and subscribe.